I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, we will discuss about the topic regularization and overfitting. First, we should know what do you mean by overfitting in machine learning. So, overfitting means when a model performs well on training data but poorly on testing data, it is said to be overfitting. That means overfitting happens when a machine learning model memorizes the training data instead of learning the underlying patterns that generalize to new data. As a result, the model shows high accuracy on training set but performs poorly on unseen data sets. This occurs because the model has become too specialized to training data and fails to make reliable predictions on new inputs. And the overfitting occurs due to a complex model that captures noise and patterns specific to training data. A complex model has larger number of parameters and high capacity to fit intricate patterns. While this allows it to capture the details of training data, it can also lead the model to learn random fluctuations or noise that don't represent general trends. This unnecessary complexity causes the model to lose its ability to generalize, leading to overfitting and etc. And these models have though it is overfitted, such as low bias, that means low learned training data well, high variance fails on unseen data, high generalization error will be there in that. That overfitted models typically exhibit low bias because they fit the training data accurately, making few errors there. However, they have high variance, meaning their predictions change drastically with the small changes in input or data. This imbalance leads to high generalization error, which reflects the model's inability to perform well on data it has not seen before. Next, what is regularization? So, regularization is a technique that use it to reduce overfitting by adding extra information or constraint to the model. It introduces additional information to the training process to discourage the model from becoming overly complex. By applying constraints such as penalties or on large parameter values, it restricts the model's ability to fit every minor details in the training data. This helps ensure that the model captures general patterns that apply more broadly. Next, it helps the model to choose simpler solutions. In machine learning, simpler models tend to generalize better. Regularization pushes the model toward simpler solutions by penalizing unnecessarily complexity. This preference for simplicity helps the model avoid learning from noise and instead focus on essential relationship in the data. Next, the goal of the regularization is not to minimize the training error, but to improve how well the model performs on unseen data. In fact, regularization might slightly increase training error because it limits the model's capacity to overfit. However, it effectively reduces generalization error, making the model more useful in practical applications. And the main goal is the ultimate purpose of regularization is to build models that maintain high accuracy not just on training data but also on test and real world data. By controlling the model's complexity through regularization, we can increase its robustness and ensure better predictive performance when deployed in practice. Next, generalization error. What do you mean by generalization error? The generalization error means a measure of how accurately a model predicts output for unseen or test data. Generalization error quantifies the difference between a model's performance on the training data and its performance on new unseen data. It reflects how well the model has learned the underlying patterns rather than memorizing the training examples. A low generalization error indicates good model generalization. Next, high generalization error indicates poor performance on new data. If a model has high generalization error, it means that the model is not successfully applying its learning to new data. This often results from overfitting, where the model has captured noise and training specific patterns instead of general trends. Such a model is unreliable in real world applications. Next, regularization strategies are designed to minimize this error. The main aim of the regularization is to reduce generalization error by controlling how flexible the model is. By applying penalties or constraints, regularization techniques encourage the model to focus on the most relevant patterns, thereby improving performance on new data and minimizing generalization errors. Next, regularization techniques overview will see. The first point is that the common regularization techniques include hints, weight, decay, ridge regression, lasso regression. Several techniques have been developed to regularize models and reduce overfitting. Hints use prior knowledge to guide learning. Weight decay discourages large weights by penalizing them. Ridge regression, that is L2 regularization, shrinks all coefficients to reduce complexity. Lasso regression, L1 regularization can shrink some weights to zero, effectively performing feature selection. Each method tackles overfitting from a unique perspective but with the same goal. What is the same goal? Improving generalization. And the first method we'll see, technique one, is the hints. Hints or properties of targets functions known independently of the training data. Hint represents domain knowledge or assumptions about the problem that remain true regardless of the training data. These could include physical laws, geometric invariants, or known behavioral patterns. Incorporating such knowledge into the model helps guide it toward more robust learning. And say, for example, in image recognition, object identity remains unchanged under rotation, translation, or scaling. How in image classification task, an object like a cat remains the same even if it is rotated or moved within an image. We can able to identify these known transformations or invariances can be used as hints to teach the model not to be sensitive to such changes, improving generalization and reducing need for large data sets. Next, uses of hints, virtual examples, augment augmented data created using transformation. Hints can be implemented by creating virtual examples, additional training samples generated by applying known transformation like rotation or flips to existing data. This data augmentation enriches the data set and reinforces the model's understanding of invariance without needing new labeled data. And next uses of another use of the hints is network structure modification, that is design the model to reflect known invariances. Another way to apply hints is through architectural design. For instance, convolution neural network CNN are built to handle spatial invariances, making them well suited for image tasks. Embedding these properties directly into the network helps the model generalize better without learning these invariances from the scratch. The next technique is the weight decay, and it adds a penalty to the loss function to discourage large weights. Weight decay, also known as L2 regularization, modifies the loss function by adding a term that penalizes large weight values. This discourages the model from assigning excessive importance to specific inputs, thereby controlling its complexity and reducing overfitting. Next, encourages the network to use smaller weights, reducing model complexity. By applying a continuous penalty, weight decay forces the network to prefer smaller weights unless larger ones are absolutely necessary for minimizing loss. And smaller weights generally indicate that the model is not overlaying on specific features, which leads to simpler, more generalizable models. Next, implementation implement a constant force pulling weights toward zero. That means Wi is equal to it is the new weight, updated weight is equal to old weight minus eta into dou L by dou A in plus lambda into Wi. This update rule introduces a regularization term. This lambda is the regularization term that acts like a gentle force constantly pulling each weight toward to zero. As a result, during training, weights grow more cautiously, helping the model resist overfitting by staying within a simpler function space. Next, third technique, rich regression. It is used when there is no multi-collinearity among features. Multi-collinearity occurs when input features are highly correlated, leading to unstable coefficient estimation in standard regression models. Rich regression addresses this issue by regularizing the solution, making the coefficient estimates more stable and reliable even in the presence of redundancy among features. Next, it adds L2 regularization norms penalty to the cost function. That means this formulation penalizes the sum of square of the coefficients, encouraging the model to minimize both the error and the magnitude of weights. Here, the lambda, no. So what it will do is here this is the loss function. The loss function is given by yi minus yi gap. This represents what this loss function, it represents yi gap is the what we are finding out, and yi is the targeted output. The y is what targeted output, and lambda is the regularization factor, and wi is the weight value. So here what it will do is this formalization, it is the sum of the squares of the coefficient, encouraging the model to minimize both the error and the magnitude of weights. The lambda parameter controls the strength of the regularization, allowing for trade-off between fitting the data and keeping the model simple. And it penalizes what it will do is large coefficient but does not set them to zero. Unlike lasso regression, rich regression strings coefficient towards zero but does not eliminate them entirely. This means all features are retained in the model but their influence is moderated. This is particularly useful when all features are believed to be relevant but require regularization to prevent overfitting. Next, finally, it helps to reduce model complexity without feature elimination. How? By applying uniform shrinkage to all coefficients, rich regression reduces the overall complexity of the model without discarding any predictors. This allows the model to remain comprehensive while gaining robustness, especially in high dimensional spaces. And the fourth technique is the lasso regression. It stands for least absolute shrinkage and selection operator. Lasso is a regression technique that performs both regularization and feature selection. It achieves this by applying an L1 penalty to the loss function, encouraging sparse solutions where some coefficients are driven exactly to zero and effectively removing the corresponding features. Next, use L1 norm regularization. That means the loss function is given by yi minus yi gap. This is the what we have predicted the output. This is the targeted output square plus lambda into wi. The L1 penalty increases linearly with the absolute value of weights. This short penalty makes it more likely for some weights to be zero, especially when they contribute little to reducing the overall loss, leading to a simpler and more interpretable model. Next, it shrinks some coefficients to exactly zero. Unlike rich regression, which only reduces the magnitude of weights, lasso can eliminate irrelevant or redundant features by shrinking their corresponding coefficient to zero. This leads to more compact models that focus only on the most influential variable. Next, it is useful for feature selection by eliminating insignificant features. That means Lasso's ability to execute variables make it a powerful tool for feature selection, especially when dealing with high dimensional data sets. It helps simplify models enhance interpretability and penalty to improve generalization by removing noise from unimportant inputs. Coming into the summary, the overfitting reduces model performance on unseen data. When a model overfits, it performs exceptionally well on training data but fails to generalize. This is because it has learned patterns specific to training set, including noise, which does not appear in test data. Overfitting thus compromises the model's real world effectiveness. Next, regularization helps to reduce overfitting and generalization. That is generalization error. Regularization combats overfitting by limiting model flexibility and encouraging simplicity. By constraining the learning process, it reduces generalization error and improves the model's reliability on new data, which is the ultimate goal of machine learning. Next, technique is the techniques which we are used hints use the prior knowledge, weight decay, penalize large weights, rich regression, L2 penalty, and reduces the complexity. Lasso regression L1 penalty does future selection. Each regularization techniques offer a unique strategy. Hints inject domain knowledge. Weight decay discourages large weights to simplify the model. Rich regression applies L2 regularization to reduce variance, and lasso regression applies L1 regularization to select only the most impactful features. Together, these techniques provide a powerful tools to build robust models. Hope everyone understood about this topic, overfitting and regularization, how to avoid the overfitting by using the regularization. The remaining things we'll discuss in the next lecture. Thank you.